optimizing control, time delay system, and FIS history, and real-time computer application for automation. He supervised more than 100 students, and he published more than 100 international journal papers. And he also, sorry about this, he also authored 2 textbooks from Speedup, even though it doesn't appear in the slide. He also a fellow of 한국공학칼리먼, and fellow of 한국과학기술칼리먼, and a fellow of IEEE, and fellow of International Federation of Automatic Control, and fellow of the World Academy of Science. And Professor Kwon is former president of IFA and ICOS, which is Korean NMO of IFA. Also, he was the president of KIEE, that's the Korean version of IFA. And Professor Kwon was the vice president of 공학칼리먼 and 한국과학기술칼리먼. And he actually motivated 10 entrepreneurship. So he encouraged 10 startups, and 7 out of 10 went already to the postdoc, which is the Korean version of NASDAQ. And this year, he has been elected as Korea's meritorious scientists and engineers this year. In order to honor Professor Kwon's lifetime influence and the contribution to the community, this series of lectures was initiated in 2016. We already invited Professor Thomas Callas and Alberto History and Stefan Boyd. And this year, well, actually every year a person who made a great contribution to system control area is invited and asked to deliver the lectures. So this lecture is then recorded and broadcast online to the public in order to distribute the knowledge and wisdom of the invited speakers. So this year, Professor Morari kindly accepted this invitation. This event is made possible through the donation by Professor Kwon and his former students. So I would like to take this opportunity to thank all of them for their endowment. And also, we thanks for the support of Korean NMO of IFA, which is ICOS. I hope and believe this lecture series continues delivery of knowledge and wisdom of the invited speaker to the young researchers of the next generation, so that they will also contribute to the community and the world in the future. This event is organized and managed by the ERC-ACI, which is the engineering research center for the advanced control and instrumentation. This center was actually founded by Professor Kwon in 1991 as the ERC program supported by the Korean government. And this center was one of the most successful ERCs. And now it is working for education and propagation of the knowledge. And here is the URL for that center. Finally, we are proud of the member of the Department of Electrical and Computer Engineering, which was served the industry and academic community for more than the past 70 years. So now I would like to introduce the head of our EC department, who is Professor Domori. So let's welcome him.
Good afternoon, distinguished participants and guests, and Professor Wook Hyun Kwon and Professor Manfred Morari. I'm indeed honored and delighted to be here today, and on behalf of the School of Electrical and Computer Engineering at Seoul National University, I would like to extend the wholehearted welcome to all participants and congratulate the Wook Hyun Kwon lecture. Dr. Kwon, Professor Emeritus of Seoul National University, has been our role model, like a shining light. He has encouraged his students to make startup companies even much earlier than the startup booming in Korea. His former students made more than 10 companies, as Professor Shin explained, among which we can find very successful companies today, such as Humans and Suprema. Academically, it is amazing that his paper published in 2001 in International Journal of Control is one of the most highly cited papers among all papers published from our department up to date. More than that, Professor Kwon has served as the president of the International Federation of Automatic Control. He was the first professor in the history of our department who served as the president of the International Society. Professor Kwon has been pursuing for contribution in academia even after his retirement. He recently published 2 books. One is Stabilizing and Optimizing Control for Time Delay Systems, published by Springer, and I think Professor Shin wanted to show these. And the other book is translated book of digital signal processing using MATLAB for undergraduate student education. Therefore, in that sense, Wook Hyun Kwon lecture series has a very special meaning for us. And it is our great pleasure and honor to have as the invited distinguished lecturer, Professor Manfred Morari from University of Pennsylvania. I believe that Professor Kwon will introduce Professor Manfred Morari, but in fact, he is so well known with his research and books and does not need any introduction. I'd like to thank Professor Morari and Professor Kwon, and also appreciate all efforts for Professor Hyun Kwon and the Engineering Research Center for Advanced Control and Instrumentation for this lecture series and arranging this wonderful opportunity of learning from Professor Morari. Personally, tomorrow is my last day as the department chair. So this is my last official activity. And it is my great honor to finish my term with this very honored address of the Professor Wook Hyun Kwon lecture. I sincerely hope all participants enjoy this very meaningful occasion. Thank you very much.
His last day, not in his life, but okay. So next, Professor Kwon is coming to the podium and to introduce Professor Morari. 이걸로 하시면
사진 안 나오나? 사진 나와.
사진 나올 것 같습니다. 다시 한번 해보겠습니다. 네, 나옵니다.
아, 그러니까.
이걸로 하시면 됩니다. 그렇습니다.
그걸로 넘어가는 거.
Dear Chairman Lee, and Professor Lee, another Lee, and ladies and gentlemen, it is my great honor to introduce Professor Manfred Morari, a great scholar in control field. He obtained diploma from ETH Zurich and the PhD from University of Minnesota, all in chemical engineering. I'll introduce his academic career. He was professor of University of Wisconsin for 4 years. Then he was professor of Caltech, very well-known university. Then of Caltech in almost 13 years. Then he became professor in ETH for 22 years before he retired. From 1994 to 2008, he was head of the automatic control laboratory of ETH. Is a very well-known laboratory there. And 3 years, he was head of Department of Information Technology and Electrical Engineering. After retired from 2016, he moved to University of Pennsylvania to become the sixth faculty fellow in Department of Electrical and System Engineering. He was the president of European Control Association from 2011 to 2013, and he was general chair of European Control Conference in 2013. Morari supervised more than 80 PhD students who are now professors in universities all over the world or hold position of a major responsibility in the industry. His research interest throughout his career, Morari and his research group were striving to develop theoretically founded tool for process system engineering, control and automation to further understanding and to impact practice. He published 2 books, Robust Process Control in 2004 or some earlier one, also version, and the Predictive Control for Linear and Hybrid System is recent one, 2017, very high citation. And the second one, only for 1 year, usually 1 year don't citation, already 450 citations. This is very good books. And 1980, Professor Morari research focused on the robust control, the principle of internal model control, so-called IMC, introduced by him, has been incorporated in all leading process control textbook and has been adopted by a number of control vendor and the major users. In 1980s, Morari became interested in control of system involving logics and constraint. Together with his colleague, he introduced a new modeling paradigm for linear hybrid system, mixed logic dynamic systems called MLD, taking advantage of rapidly increasing computer power. They showed how model predictive control based on MLD system model can solve a range of challenging control problems in many applications. The ABB's current mill and electrical drive control system are based on this technology. Morari research is internationally recognized. Analysis technique and software developed in his group are used in university and industry throughout the world. Here's a very high citation, over citation, 73,400 some. This indicates he's truly outstanding researchers. From this activity, he received many awards and honors: Ekman Award, Raji Award, Bellman Contracts Award from American Automatic Control Council, and Colburn Award, the Professional Progress Award, Cost Division Award from American Institute of Chemical Engineers, Control System Technical Field Award, Border Lecture Prize from IEEE, a Nyquist Lecture, and Rufus Oldenburg Medal from American Society of Mechanical Engineers, and IFAC High Impact Paper Award from IFAC, from his paper. I would like at least one of this one, but he has many, but I couldn't make anyone. Anyway, this is surprising. This is a record shows his outstanding researchers. Finally, he became fellow of IEEE, fellow of IFAC, fellow of U.S. National Academy of Engineers. This is an honor. A fellow of UK Royal Academy of Engineering. And okay, this is the end of my introduction of Professor Morari, a great scholar in control field. Let's welcome him.
Good afternoon, and I look at the clock here, and I think that even the Swiss could learn about you. Even the Swiss could learn about your punctuality here on the second. Thank you, first of all, Professor Shim, for arranging the talk, arranging the program. Thank you also for Professor Kwon. And they did not only arrange for this lecture, but also for a very busy program over the next 10 days, which my family and I very much appreciate. Thank you for this kind introduction and this generous praise. But today I feel we are not here to celebrating my accomplishments. We are here to celebrating Professor Kwon, whom I have known personally and admired for the last 25 years, at least that's what I remember. Professor Kwon, as you heard, has made a series of pioneering research contributions, and he has shown exceptional professional leadership. The IFAC presidency was mentioned, as well as the presidency of a number of Korean professional societies. And very important, at least in my eyes, together with the students and collaborators, Professor Kwon has had a deep impact on the evolution of technology in Korea through his students and the startups they have formed. And I was extremely happy.
I'm really sorry for the interruption. So recording man says you need this microphone to make a record. Sorry for the interruption.
Okay, so both or just one?
No, just
okay.
use that one. So let me just turn off this one.
That's fine. Okay. Thank you. So now I feel more like a movie star. And I was extremely happy that this year Professor Kwon was one of the youngest persons to be chosen Man of National Merit for Science and Technology in Korea. So it's a great honor for me to be invited here. And I thank you also for joining me here in this event. You know, in preparing the lecture, I was thinking back and say, when did I meet Professor Kwon the first time? And I can't date it exactly, but I think I'm coming very close to it, and you will recognize some of the events. So first of all, I think 25 years ago, almost to the day, it was the first time that I was in Korea. I attended a symposium in Gwangju on process systems engineering, and if you look at the topics that I covered in my keynote lecture on current directions in process control, you will already find mentioning of model predictive control, for which the theoretical properties just started to be understood around that time. But I'm not sure that at this visit I actually met Professor Kwon. But the year afterwards, there's no doubt, because he actually organized a short course on model predictive control. And I was invited here as a lecturer in 1995. That was just shortly after I had moved to Switzerland. And not only that, I actually have some pictures from that event. We all changed a little bit over this quarter decade. So you see Professor Kwon here, and I think this is Professor Michalska, a student of Professor Main. And this is Professor Mosca from the University of Firenze. And then there's another picture, more a group picture, and here you also see MC Yoon, and you see Sungwon Park, and so a number of other people at that time. So we all changed, but this is certainly, so I have known Professor Kwon for at least 24 years, maybe even longer. Let me give you a start with the message of my talk. Control has always been limited by computational resources. If you go back, you can go back to analog control and pneumatic elements in the control loop, etc. And as more resources, computational resources, became available, ingenious practitioners found ways to make use of them. And later researchers provided the theoretical foundations, and I think MPC is the ultimate development of this evolution. In terms of computation, computers started to play a role in control in the 1960s, so about 50 to 60 years ago, and what's shown here is the IBM 1800, which was probably the first commercial control computer, or at least the first widely used control computer. But the introduction of this computer actually did not change control practice, at least as we experience it, say, in the chemical and the refining industry, because for a long time after that, computers just mimicked or were digital implementations of analog algorithms. And this is a typical flow diagram from this time, a piping instrumentation diagram, and you will see PI controllers with simple nonlinear elements and logic. And when I worked for Exxon Research Engineering as a young assistant professor on a summer job in 1978, this was largely what I dealt with. Some very simple digital computers and still analog in spirit control software. And what was not known to me at the time, and to most people, that at the same time there were people at Shell, so the competing oil companies to Exxon, and they were working to take advantage of the newly available computer power in industry in entirely different ways. And there was a person mentioned at the bottom, Charlie Cutler. He was a PhD student of the University of Houston. And in 1969, and he sent me all this documentation, he conceived of the idea of what he called dynamic matrix control, which is effectively the same as model predictive control. And he interrupted his studies, and for more than a decade, he joined Shell to implement and test DMC, as he called it, in refineries. And I think he must be credited for having started a control revolution, at least in the oil and chemical industry. So what's MPC? Probably all of you here have heard this, and it works as follows. You take measurement of a state, and with this state as the initial condition, you solve a trajectory optimization problem. That means you determine an optimal sequence of inputs that minimizes some cost functions, so for example, sum of squared of errors. And then you implement the first one of those computed sequence of moves. You wait for the system to react, see in the second line, and then you take a measurement again, and that cycle repeats itself. And this idea and the concept had tremendous impact, at least at that time, in the process industries and the oil and chemical industries. And this review paper, you probably cannot see all the details, lists in the year 2003, 4,500 industrial applications. But most of the applications at that time were in the oil and petrochemical industry, because these processes are slow enough to allow the necessary computation, this online trajectory optimization, to be carried out in real time with the computer power that was available at that time. And while there was great enthusiasm among the practitioners, and Cutler is the leading proponent, the theoreticians were largely not impressed, and they snickered at this work on dynamic matrix control or model predictive control, because they viewed it as ad hoc, not rigorous, not founded in theory. And actually I ran across this quote from Warren Buffett recently, He's probably the world's most successful investor of all time. And tongue-in-cheek, he summarized the attitude of the academic community towards his investment approach and has some parallel with MPC. And he said, people say, well, this may work all right in practice, but will never work in theory. Okay? And I think with MPC, the attitude was very, very similar. And in the 1980s and actually starting in the 1970s and 80s and 90s, the theoretical foundations of model predictive control started to emerge. And certainly the first paper in this direction was the paper by Professor Kwon and Pearson, I think when he was still at Brown University, where simple stability conditions were derived for linear systems with receding horizon controllers. And their pioneering results are cited in essentially all subsequent papers on the subject. So for example, also in the landmark paper by Kerty and Gilbert, where they extended the results of Kwon and Pearson to systems with constraints. And this paper by Kerty and Gilbert contains all the main ideas, and the following maybe dozens or hundreds of papers on MPC theory, just added details, important details, but just details. So for example, the paper by Rawlings and Muskie focused on linear systems, and the summarizing survey paper by Main, Rawlings, Rao, and Skokert is actually the most cited paper in MPC. And not only that, it is by far the most cited paper in the control journal Automatica ever. And it is that by a large margin. A large margin, I mean like thousands. Okay. So that gives you some sense of the impact and the theory of MPC had following on the practice that had started in the 1960s and 1970s. So what were those theoretical results and the contributions? So first of all, what people showed is a property called the recursive feasibility, and that's if a control action is feasible at the initial time, it will be feasible at all future times. And the second property is asymptotic stability. And the papers that I showed on the last slide showed how to effectively synthesize MPC controllers with these guarantees of recursive feasibility and stability. But those results come with a catch, because they assume that you can solve this real-time trajectory optimization problem online with at least some specified epsilon accuracy. So you may also wonder, what was the impact of all this theoretical work? People started using it in the 1970s. Theory came later in the 70s, 80s, and 90s. So what was the consequence of those theoretical developments? So first of all, from a practical point of view, this theoretical analysis improved the implementation and the maintenance of the algorithms and the software, which is a prerequisite to do anything at scale. And the second, from a theoretical point of view, MPC is probably the only control technology that allows controllers to be designed for large constrained systems with stability and performance guarantees. And the third point, it really brought this academic responsibility, respectability. And this is important because before that, the leaders of the control community tended to brush away model predictive control as some trivial ad hoc approach without justification. And finally, this theory helped to educate students and engineers in that technology, which was extremely difficult going back to the original work, for example, by Cutler. And when Frank Allgöber, who is now IFAC president, was an assistant professor at ETH, he organized a workshop in a center that is owned or at least rented by ETH in southern Italy. And he organized a conference on nonlinear model predictive control. And if you look at the proceedings from that conference, you will find that all the applications that I mentioned there were all in process control, in oil, chemicals, refining, etc. And then 10 years later, Frank Allgäuer was not at ETH anymore, but he organized another conference on nonlinear model predictive control. And you look at the applications that people were working on at that time, apart from the theory, and you will find now process control has essentially disappeared as an application, and people started focusing on applications in other areas, namely automotive, power electronics, as two examples. So one may wonder, what happened between 1998 and 2008 to lead to this dramatic change in the applications that were addressed with model predictive control. One reason is almost obvious: computers became a lot faster. And there were also faster optimization algorithms that took advantage of that computer power, and that took a jump in those 10 years that I mentioned. And the third thing is that in addition, people concentrating on writing and preparing dedicated optimization algorithm to model predictive control. And I will say now a few things about each one of those items. So the first one, it may be interesting just to reflect how much faster, especially for the younger audience, especially how much faster computers got in the 30 years that are addressed here in a talk by Jeff Linderoth from the University of Wisconsin. So he looked at the period from 1988 to 2017, and he said, roughly in this 30-year period, computers became faster by a factor of 17,000, but algorithms, he's talking about mixed integer programming, algorithms became faster by a factor of 150,000. So it's not just the computer hardware, but it's also new ideas that were introduced here. So you multiply that together in a somewhat simplistic way, and you get a speed up in 30 years by 2.5 billion. And clearly, those are not just quantitative changes, but they are qualitative, because it became possible to solve new problems that people hadn't even thought about. And what that speed up means, down here it says, it means the speed up that in 1988, when you tried to solve a problem that may have taken 124 years, nowadays it takes 1 second. Okay, so that's the speed up that was experienced by a combination of algorithm and computer hardware changes. And the last thing in this list of what happens with new algorithms, and specifically MPC, that I want to discuss, and just to recall for you, and remember, in order to get those guarantees from MPC, we have to solve this real-time, we have to solve this trajectory optimization problem in real time. And if the controlled process is fast, and if the computing power is somewhat limited, doing this last step is a serious challenge. And so around 2000, I would say that started to be addressed, and addressed in two different ways. One is offline, and that means you don't do that optimization online, but you pre-do the optimization and then just use the results in the control. Or the second, to do the optimization online and develop new algorithms that are specifically dedicated to MPC to do this optimization fast enough. Around 2000, Alberto Bempera, who was mentioned by Professor Kwon, and also other groups, as mentioned at the bottom of the slide, found out or realized that yes, actually for small systems at least, we can put all that optimization not online but offline, pre-do the optimization. And what is the controller that we get from it? The controller is actually a piecewise affine function of the states. Okay? So if you didn't have constraints, this would be just a plane, and it would be typical linear quadratic regulator that you learn in your classrooms. With constraints, it becomes piecewise linear or piecewise affine. And so what this means in terms of the online implementation, basically you have two steps. The first step is to recognize in what polytope here that defines that piecewise affine surface is your currently measured state, and then to evaluate that affine function that is stored for this particular polytope. And so that means the online complexity of this operation is governed by that first step, finding in what polytope that particular measurement point is located, and if this is a function of how many of those polytopes you have, and if it's reasonable, you can then implement this whole algorithm step, finding and doing the affine evaluation. You can implement it in milli or microseconds. And that technique, we were first maybe too enthusiastic about it, is suitable when the systems are reasonably small, meaning fewer than 5 states. Then you have a simple lookup table, and you can evaluate this maybe in a microsecond sampling times. But if that's not the case, if you have larger system, let's say up to about 10 states, then you can handle it with some approximate explicit methods, as it's called here, and beyond that, the control law becomes excessive, and we have to excessive in terms of the number of regions that are generated, and we have to return to online optimizations. So in the online optimization methods that I have listed here on the right side, we have the first order method that what they started with, and then interior point methods that are tailored specifically to model predictive control, and they allow millisecond sampling for systems with essentially any size. And so over the years, what we together with other groups have developed is a so-called multiparametric toolbox, where you can specify the problem in some design language, YALMIP, or this hybrid system description language that we developed. And this returns then the software either exact, explicit model predictive control or some lower complexity, approximate solution in the form of executable C++ code. On the other hand, there are some packages for doing the online optimization efficiently, and authored by 2 of my former graduate students, Stefan Richter and Alex Domahidi, and there's some method for using some software for using first order method, second order method, constraint quadratic programs, and also second order cone programming, actually work that was done together between Alexander Domahidi and Stephen Boyd, who was here last year's Kwon lecture. And in our lab at ETH, we have applied the tools to a wide range of problems, which vary from very relatively slow, energy efficient building control work that we did together with Siemens, up to control of multi-core computers, the thermal management. And in between are, on the slower side, applications in the automotive industry, so electronic throttle control and traction control, and on the faster side, applications in the power electronics area. Only recently, and you saw that mentioned in the summary, ABB introduced a new drive for high performance motor control, and they advertise it as containing MP3C, which stands for Model Predictive Pulse Pattern Control. And the development of this, the development team included many people who had been members of our laboratory at ETH, and that's where this development started. The ETH spin-off, Embotech, co-founded by Alexander Domehiri, distributed Forces, the Forces software, and is now used across the different industries by 150 partners in 35 countries. So what I talked about now is the past. So if you work on model predictive control, you probably know most of it or some of it. And you will probably agree at this point that it's fair to say that by taking full advantage of the ever-increasing computational resources that we have available, MPC has become the most successful control algorithms in the last couple of decades, and maybe the most successful ever after PID control. At least you will not replace PID control at the lower level control tasks. So then there are a number of research areas that people are looking at and we are looking at, and there are many papers to be written, many developments made, but it's not totally clear that in those areas ranging from robust MPC, stochastic MPC, output feedback MPC, it's not totally clear what will be the practical impact that you can expect from those developments, notwithstanding the theoretical contributions. On the other hand, I strongly believe that in those last two areas, there's a lot to be gained for eventual applications. And one was mentioned, the hybrid or switch system. So for example, there's great interest in robotics for problems with contact to model those as hybrid systems and to do the optimal control computation in this way. Only you can't do it, it's too complicated. Okay, it's too complex at this point. So there's clear practical need for doing something there. And the second thing is, you read every day, I'm sure in Korea, even in Switzerland, US, you read about machine learning, you read about artificial intelligence, and you read very impressive success stories. And as a control engineer, you ask, can we afford not to get involved in this area? And at least, I don't know if you read Dilbert, at least Dilbert doesn't think we can avoid it, so I'm going to read it to you. So on the left, Wally, I need you to head up our artificial intelligence project. You will have no budget, no hope of success, but I just like saying we're working on AI. You're completely useless, so it's a good match, and Wally responds, I won't let you down. So, no, we do not want to pay only lip service as suggested here, but we want to analyze and understand what learning can do for dynamics and control. And you may know that at the end of May, so just a couple of months ago, there was a workshop at MIT. Actually, it's the first workshop in a series. Second one will be at Berkeley next year in June. That is dedicated to this topic of learning for dynamics and control. And it was attended by 400 people, it was sold out, and I was actually invited to deliver the opening address. And I decided to provide a practitioner's perspective in a paper co-authored by a postdoc of mine at Penn, and also a new graduate student, and two professors, Hamid Hassani and George Papas. And I tried to provide a practitioner's perspective because that's something I know about. So I took a look at the general features of learning controllers, independent of the particular flavors. And one of the questions I tried to ask is, should we have which is all over the literature, should we have a model-based approach or a model-free approach? And if you were an early student of adaptive control, this is equivalent to saying in the past, should I have a indirect adaptive control, or should I have a direct adaptive control? And first, so my question that I ask the audience is to say, okay, if you do not have a model, okay, like what's implied in a model-free method, how can you eventually verify the performance of the closed-loop control system you're designing? And if you cannot do the verification, it's highly unlikely that anybody in industry will adopt this methodology. On the other hand, if you do have a model, then maybe you should use the model directly and not discard it and go with a model-free method. So that's a question that put to the audience. And the second question about those methods is about policy learning based on reward functions. So you have some objective function, you learn the policy from optimizing this reward function. We call it objective function. And this is not a new idea. This actually, University of Minnesota was mentioned when I took a course from Rutherford Aries on optimal control. This was mentioned, but it was mentioned as a curiosity because of two reasons. Number one is cursive dimensionality. It immediately blows up for even small systems. And clearly, since I was a grad student 40 years ago, a lot have changed, and this has been addressed to some extent. On the other hand, you look at specifications for controller as I would see them from industry, and I have some examples. There is no way we are going to guarantee that those specifications will be met in this approach, just optimizing a reward function. The reward function would be impossible complexity to do it in this way. And my questioning, of those methods is maybe you may say, I'm not competent to answer this because I'm not enough knowledgeable. I may be opinionated, but it's not only I who ask these questions. Okay, and I refer you to a very interesting paper that was published on Wired just 2 weeks ago, where there is a serious question of the AI and in particular reinforcement learning in the context of applications beyond the game applications that we have seen so far. On the other hand, the positive outlook is maybe we can combine our knowledge of control and AI, and the proposal is to work on identifying discrepancy models, meaning not discarding our model knowledge altogether, but using AI identifying models that describe the difference between our model and the real observed behavior. And then to use this discrepancy information to actually do a robust MPC controller design. Why MPC? Because as I said throughout the talk, that gives us the performance guarantees that we need to have for applications. And so I want to, in this last part of my talk, I want to introduce 3 ideas. That means research project in progress that I'm involved in, at least in 2 of them, at the University of Pennsylvania, that go in the direction of combining ideas from artificial intelligence and our control knowledge, like model predictive control. So let me start with the first project, which is an almost obvious thing to do, and that is looking at how to do MPC faster for online implementations. So maybe instead of doing this optimization, we should just approximate the MPC by a neural network. And remember, I want to have those properties of MPC. That's the power that I have those guaranteed performance characteristics, recursive feasibility and stability, but that requires this optimization to be done online. So what's the idea? We will replace the online optimization with a trained neural network. But however, if we do that replacement, we will most likely lose the guarantees that come with the model-based MPC, that is the online optimization. So in order not to lose that, what the graduate student Stephen Chen suggested is to combine our online optimization methods and the neural network in an organized fashion, namely offline, first to generate a data set using correlated sampling and to fit a neural network, and then online to use that neural network output not as a solution but only an initial guess or a warm start for an optimizer, which we can run then efficiently to get again the guarantees that we expect to get from MPC. So the idea is to combine deep learning with traditional optimization to provide the guarantees by construction that also scales to large systems. By the way, this here, we had this idea in 1999. I remember even the office discussion with Alberto Pemperat and Giancarlo Ferrari Tecate at ETH. And after 5 minutes, we gave up because we said computation absolutely hopeless, that we can do this neural network fitting to give us an MPC controller for a size of a useful size. And here's one experiment that was done by the students that I mentioned on an example that Stephen Boyd introduced, and it's a good example for testing optimization, namely combined masses. So in this case, it's 18 masses and 9 actuators. State dimension is 36. And then to do an MPC learning a neural network based on the MPC results. So what scales are we talking about here? Okay, so this means it was trained on optimal trajectories for 2.5 million initial states. Okay, the network that we are looking at eventually has 1.7 million parameters, and training, at least by my conservative views, is a major effort, which means 40 hours on some NVIDIA Titan X GPUs using TensorFlow. Okay? So how good is what we get? Actually, yes, we are still experimenting. It is effective, and the histogram here shows here a number of iterations, and here what fraction of the problems needed how many iterations. That's about 12,000 cases that were investigated here. If we want optimality, okay, which is the blue curve here, then the neural networks allows me to remove from blue to orange. So that's the reduction in the number of iterations. If I'm happy with a epsilon optimality, suboptimality criterion, that allows me to reduce the iterations from the red to the green histogram. So yes, if you look at this, method reduces iterations by 98%. If you look at the computation time, it's maybe 90%. But you look at this and you say, yeah, maybe it's interesting, but is that type of approach useful? And is this the best way of introducing complexity of MPC? And I'm not sure. Actually, we wanted to do exactly this, as I said before, a long time ago, but we couldn't. And so let me suggest something slightly different. Rather than guaranteeing MPC properties by design, we are going to combine offline learning and online active set strategy in this conservative way. Rather than doing this, we just fit some neural network to MPC, and then in the second step, we check the performance. And that's what I want to describe next in this topic, robustness analysis of learning-enabled controller. And actually, we are involved through Penn in a project by DARPA on assured autonomy. And Boeing is one of the industrial partners on that project. And we discussed learning, and there was a representative from Boeing, and he said, no learning components on our airplanes. So maybe you're happy to hear that. But what they mean is no learning in real time. They are considering to have trained neural networks, and this is meant here with learning-enabled components, but not the learning on the real time, but pre-learning before they're implemented. And clearly, when they use a complex neural network somewhere in their control loop, they want to make absolutely sure that if there are 100,000 parameters in this network, that this network does not display some unexpected behavior. And so that's the objective of that research project, to do safety verification, robustness analysis of neural networks via some relaxation approach, which I will describe, quadratic constraints and semi-definite programming. So what's the idea here? The idea is that let's have this neural network. Let's take this point in the input space, and that's mapped to this point here in the output space. So and if you have this blue set of perturbations of the inputs set, and we want to make sure that the output set, these blue perturbations here, satisfy some safety boundary. Okay? So this is our question. Does the network guarantee the safety that if I have some perturbation of the input, the output does not ever cross the safety boundary? Now, very often networks in the literature are judged not by this type of problem, but they're just they are judged by image classification tasks. And so what would be the image classification problem that we want to address here? We would associate, for example, this input point with the input point vector with the image of a dog. And then we would have these fixed neural networks, and it would be mapped here to this point. And according to this classification boundary, it would be classified as a dog. And what we want to make sure, if our input image is disturbed a bit, as indicated with this blue region here, then the output set would still, for any of those points, give you a dog as the classification reply. That would constitute a locally robust network. The alternative would be that actually the image set nominally classifies in a dog, but actually some of those perturbations of the input set would lead to a misclassification, and the image would be classified as a cat, and you want to have a guarantee that the neural network does not suffer from this deficiency and would be called not locally robust. Or more general, we want to guarantee that the output set Y generated from this input set X is inside some safe set denoted here with S. It's a study, it's an example studied a lot by a lot of people, a lot of groups in the literature. And not surprisingly, it's an NP-complete problem. And there are special simple cases that you can solve exactly with reasonable effort, especially if those activation functions are rectified linear units, and if those output set, the safe set, is polytopic. And those are called exact verifiers. And if you cannot solve it exactly, there are many methods that have been proposed which can check if some over-approximation of that output set is inside the safe set. And there's a very nice survey paper referenced here. What we do is something different. We use a different relaxation method. And what this relaxation method allows us also to analyze closed-loop behavior with the neural net of a part of it. And I should reference here the group at Stanford who has used a similar approach as we did. And I will not discuss in detail this relaxation. If there are questions, I can do it afterwards, but this gives you kind of a result that we have obtained. Here, what's the comparison is we look at the output set, and the output set is the blue set in all those cases. And we look at our over-approximation of the output set that we find through this relaxation, which is given by the red region surrounding this output set. So it's a conservative approximation of this output set. And then in blue is the competition, which is this Stanford group that I mentioned on the last slide. And what's compared here is networks that have 2 inputs and then several layers with 100 nodes in between, and then 2 outputs. And when I say several layers, 1 layer, 2, 4, 6, 8, 10 layers. And what you see pictorially, that our approximation, first of all, is deteriorating as we increase the number of layers, increase the complexity of the network, but still our improvement compared to the method from Stanford is retained. But this, as I said, is work in progress. The last thing I want to talk about is this discrepancy model learning. And the title here is Gaussian Process-Based Model Predictive Control. So we learn about the model uncertainty, and then we use this uncertainty in an MPC controller to solve some control tasks. And that is work that was actually done by Professor Melanie Zeilinger. She was a former PhD student in my laboratory and is now a professor at ETH. And I will just give you the basic ideas, and then I will complete with a movie so that you can see the performance. So what is the idea of this Gaussian process learning, uncertainty learning? The example we will actually look at is some model race cars. And what we want to do is we want to autonomously steer those model race cars. And at the end of this section, we will also apply the methods to real electrical race cars. So the assumption is we have some simple models of those cars, but they are inaccurate. And they're inaccurate in the sense that we do not know the model parameters, or we do not know even the structure of the model. And what's particular source of uncertainty are tire models. And tire models are notoriously poor, and also they may change over time as the wear of the tire goes on. So what we want to do, we don't want to learn models from scratch, but we want to use whatever we can about tire models, and then we want to improve those models and adapt them starting from the basic physics. So in this case, our function f here is not accurately known, and there are also some unknown disturbances. So what's important that we do not just want to learn the model, but we want to learn the residual model uncertainty. And the description that we use here is Gaussian processes. And the Gaussian processes Gaussian process regression is a non-parametric data-driven framework for nonlinear regression. And so a scalar Gaussian process is a probability distribution over functions such that every finite sample of points is jointly Gaussian distributed. So that's just a short characterization of those Gaussian processes. And this is used as a mechanism to describe this uncertainty that we observe in our model. So the primary model mismatch, as I said, arises from tire forces. complex variable. Those tire forces have mostly an effect on the velocity states. So for example, the yaw rate that is plotted here. And also what's plotted is the residual, the unmodeled, what's actually plotted here is the residual, the unmodeled yaw rate. And in light blue shows the Gaussian process prediction of this unmodeled model uncertainty. So what's the consequence of doing the design of MPC using the nominal model plus the Gaussian process uncertainty? Here you see a comparison for those model race cars. On the left, nominal model predictive control. On the right, Gaussian process model predictive control. The first you see just by eyeballing is that you have much more consistent behavior, not so many different trajectories. If you use the Gaussian process model predictive control, you see from the statistics at the bottom, it was also possible to speed up the time it goes around the course, and the solution time is makes this implementable, namely it's less than 20 milliseconds in both cases for nominal MPC and the Gaussian process. And we also had then, after those model race cars, we had a student team doing the master thesis using the same concept on a real electrical race car where the student association in Zurich participates in races. And two students, Juraj Kapzan, he was a graduate student who did, or a master student, and Lukas Herring is doing his PhD and will actually complete his thesis in a couple of months. So instead of giving you the details about this myself, I will refer to a movie that where Alexander Linninger will describe what they have done in their application to this electrical race car.
In this paper, we present a learning-based model predictive control architecture for autonomous racing. Accurate vehicle models play a key role in controlling autonomous race cars driving at the limit of handling. When a model is inadequate or incorrectly identified, the resulting control policy can cause dangerous behavior. We present a technique to correct the model discrepancies using Gaussian process regression. Data is collected online and the vehicle model updated during operation. The learning control framework consists of two modules, both running on the vehicle's main computer. The MPC model receives the state estimates derived from the sensor measurements and uses this information together with the track layout and the vehicle model to compute the control inputs. Additionally, the model errors are computed from the state estimates and sent to the model learning module, which successively computes improved models for the MPC. Finally, the control inputs computed by the MPC are sent to the low-level control unit, which runs additional torque vectoring and traction control. This clip shows the framework in action. We start by using a nominal controller for initial data collection. This controller is unable to make use of the full potential of the race car due to model inaccuracy. We also visualize the MPC prediction and the collected data points. The learning-based controller is enabled at the end of the second lap, and we observe successive lap time reductions due to the improved model, as this allows for more aggressive driving. In the 8th lap, we see the final result of the learning-based controller, achieving a significant lap time reduction, while safety of the vehicle is ensured at all times. The more aggressive driving is clearly visible from the video. The MPC prediction now includes the model uncertainty, resulting in safe driving even when you push the car to the limit.
So one thing I should mention, just to put that in perspective, so for localization, they use particle filters with LiDAR and vision sensors. And the measurements is those colored cones that you saw on the track. And initially, before those learning runs were done, there's actually a mapping phase where the car is driven around the track autonomously very slowly in order to develop the map, and then the localization is done, as I mentioned, with this particle filter. Conclusion. 50 years exactly since Charlie Cutler put forward his thesis where he presented dynamic matrix control. And in those 50 years, I think it's clear, not much of an argument, that MPC has moved from this thesis proposal to a most widely used advanced high-performance control method. And what's the reason for the success? Number one, it's intuitive. You know, this receding horizon concept is very natural. The second, in principle, it is general. Okay, obviously, the complexity depends on the type of model you have, linear model, nonlinear model, hybrid system, switched model. They all give rise to different optimization problems, but basically the same concept for all those cases. The third issue is that because it uses that model, the designer can put all his or her knowledge in that model, and that the method takes advantage of all that knowledge that is encoded in the model. And lastly, obviously, that we have a method that in principle can give you guaranteed satisfaction of the specifications, okay, for all those classes of systems that I mentioned. And there's really no other method that can come even close to it. So what are the remaining challenges? And I mentioned one is clearly the computational issues that arise in the context of switch systems. We can do simple switch systems, but for example, Russ Tedrake Robotics at MIT uses very much those methods, but they all hit computational boundaries. So what to do and how to address those complexities that arise for complex, that would be an important, not only theoretical, but important practical challenge. The last thing here, learning and adaptation. I mentioned some crude ideas on how we can introduce the many developments that have been going on in artificial intelligence and machine learning, how we can use those in the control context, but we really have scratched only the surface. But the important thing is we don't want to throw out the control and just adopt those technologies. We want to combine them in a constructive way, our knowledge with control, with the new methods and methodologies that were developed in the machine learning and artificial intelligence community. And with that, I want to thank, in particular, Professor Kwon, number one, for the pioneering contributions, and I should say that actually his stability result with having a terminal constraint 0 is the only one that is practicable for the more complex system up to the present day, because the other concepts like invariant sets for most of the systems I mentioned here can't be computed. So this is the only practical answer. And I also want to thank Professor Kwon for the continuous support and belief in this model predictive control area. Now it's easy, but at the time that he worked on this in the 1970s, this was not an obvious route for people to follow. And last but not least, without his interest, I wouldn't be standing here today and delivering this lecture to you. Thank you very much.
Thank you very much for very interesting talk and for sharing very impressive results with us. Okay, so it's time for asking questions and sharing our opinions with the speakers. So if you have any comments, questions, whatever, please raise your hand and we will deliver the microphone to you. As you know, this lecture is recorded, so the only benefit why you are here is sharing your opinion, to ask questions.
And I have to challenge you, okay? Because I remember 24 years ago when I gave this short course, okay? There were many questions. And not only that, actually the questions were extremely good. And my suspicion is still that for the students to attend that course, they first had to pass an exam from Professor Kwon and then they were admitted to the course. That's why they were so qualified to answer the question.
Okay, so please raise your hand. Yes, from Hyun Kim, please.
Thanks again for your wonderful talk. I have a question about the third part of your future perspectives on how MPC will evolve. And I was wondering why you listed Gaussian process as a tool for the overcoming model difference. I mean, there are multiple functional approximators, and
Definitely.
I'm wondering why you chose that one.
No, I think this is what has been done, and has been done by several groups, but actually, I may have skipped that slide, but there were a number of other approximations used as well. I think it's probably a matter of what skill people have. I think also the Gaussian processes, as you have relatively few data points, etc., this is good. If it's many data points, it doesn't scale correctly, so it is limited in that sense in terms of the applicability. I think I would not give this particular preference. I think the main message was you shouldn't try to identify those models from scratch, but you should put in whatever you know a priori and then just use those identification methods for the rest. And I think what to use will depend on the particular application. If I came across to saying this is the preferred method, no, this is what was used. I'm sure other methods will be developed and this will become better than what I showed.
Thank you. That clarifies my.
Other questions? Yes, Professor Stefan Go, please.
Hi, thank you for a good talk. So it looks like MPC is getting popular again nowadays, and I think it's especially related to machine learning and many AI technology. And what do you think the reason for that? What kind of component MPC is have a good match with machine learning, like dynamics or modeling? What kind of component is the matching point with machine learning?
I think it really depends on the problem, okay? And so first of all, the ability to handle large data sets that we now have didn't exist, as I mentioned, 1999 when we looking at using neural nets. Okay, so at that time you couldn't train them, the complexity you couldn't handle, etc. So this is definitely one issue. The second is, and there I should put a little question mark on what I stated or what I skipped. I said, why would you use a model-free method to learn the controller? Because you need to do the verification. So if you have the model anyway, why do you use a model-free method? Okay, and this was a simplistic statement that I was actually at MIT when I made this was then corrected. Why you would do it is because sometimes and very often, for example, in the robotics cases with contact, the controller that you get without that direct learning is too complicated. Okay, so what it would enable it is this learning, the model-free learning, is to actually, hopefully, get a simple controller, relatively simple controller for an underlying complex system. Because MPC, there's a direct relationship. You have a complex model, you have a hybrid model, you get this hybrid controller, you have this relationship between the complexity. So the approximation capability of this learning would help. Just in general, I think how the two methods can benefit from each other. On one hand, you have learning methods which in MPC up to now played a very small role. Okay? There's very few, if you look at learning MPC, adaptive MPC, there are papers, okay, but there are very few papers. And you have to ask why. Okay, why did people not do learning for MPC earlier? And we can discuss, there are a number of reasons that may hold. Okay, so for example, learning all the time is very difficult to do. We should better have just some stop and then relearning, because for safety reasons. It may be that the applications people use learning MPC are not worth doing. Okay, so it goes a lot of complexity, but you don't need it. So there are many reasons why learning may not have been used in MPC. So that's one thing. From the other side, from the learning side, I think to throw out models altogether and not to have methods that have any guarantees will limit the applicability. I think, at least for the problems that I've worked on in a number of industries, you want some guarantees. Okay, maybe the learning should be used only in the automotive side for the environment and not for the vehicle. So I think those are the two holes. So one, MPC, no good learning abilities, machine learning, not much in terms of guarantees. And I think the merger of those two may bring solution to both of those problems and make progress on both those problems.
Thank you for my explanation.
So next question goes to the Professor Jongmin Lee. Jongmin Lee.
Thank you for your insightful presentation. I was very impressed that you were still reading articles even 2 weeks before. So that was
a good comment. I will reply to this.
Okay. Going back to the issue of the model-free learning and model-based learning, I've been working on this reinforcement learning approach for control for many years, and I also agree with you that we should not abandon the model. But on the other side, we can use the model. So I think the MPC, the main drawback is to solve online optimization over multi-horizon. So what you have been showing us is that getting the data and refine the model still. But the other side is that we can probably use the model for transition in solving dynamic programming, where we compress this multi-horizon optimization into single one. Then the data can be used for refining the value function, cost of function. So what do you think about
for sure. It's very closely related, and actually I think to use the model, okay, even if it's very complex, but just use simulation, okay, in order to do training. I think this is much more promising than doing training on real data, okay, for many reasons, for safety, for data efficiency, etc. And in this case, when you use the model, I think it makes a lot of sense, and we can discuss separately, but to actually try to do, let's say, a Q learning, which is very similar to, let's say, MPC one step plus rest of it cost to go function formulation, to use this, or maybe two step, and to use this in combination is definitely a promising way to go. So I agree, and my statements were here a little bit provocational, and if that's what caused your question, very good.
Yeah, I think people are now, getting the sense that the model should not be abandoned, especially in process control.
Definitely, yeah. But let me comment a little bit on the 2 weeks.
Yeah.
Okay. Because it is okay. This is just an article in Wired. It's not science. It's not science. Okay, it's not science. But frankly, I am, I should say, I hesitate to use what adjective. I'm impressed, I'm scared, I'm disturbed, okay, with the current way, and maybe I'm too old, in the current way of how publications are done and how research is done, okay? And so what do I mean? We put, as you saw there, we put those papers on archive, okay? In the past, you would submit the paper, you would get things back, you would have a year before it was published. Now, within hours, okay, you get comments from people. Okay? Within hours. Within a week, somebody published some other method that isn't properly compared, okay, and you can't really reproduce the results. All this goes into archive, all this gets cited, okay, without proper examination. So probably something useful will come out at the end because there is just so much activity by so many people at such a high speed. But in my eyes, it was a dramatic change, okay, in speed. And it puts a lot more pressure, especially on young people, to find a problem, okay? And actually our dean, Vijay Kumar, at some point commented and said, okay, in the past, if I look at my history, what did we do? We developed some method and then we took enormous efforts to convince industry to use them. Okay? You would go out, you would say, okay, this is the advantage, and you would try to convince, and only very few things got used. And I'm sure you know that all from yourself and from your history and so on. Okay? It's totally different. Okay? Now it's the following. You develop something that has any hope of use, it will be picked up by some company extremely quickly, let's say Google or Facebook or Amazon, and they will throw at it teams of people excellent people that will push this forward in a speed that you have no hope of competing. And so the search now is not to find and convince some company to use your stuff. The search is, what can I do research on that it's long enough of a horizon they will not be interested in. It's a total reversal of the situation. And I don't think I'm exaggerating.
Thank you very much.
Okay, so the next question goes to Professor Chung-Shin Chung, who is the president of MIPS.
I'm very sorry I was late. I had an unexpected meeting before your talk. I missed half of your talk, so I couldn't know what topic was covered. My question is, based on my experience with MPC and CNN, I think Frank Albor recently focused on how to use CNN and the MPC. He was supposed to give a talk in a Chinese control conference last month, but it didn't cover due to the short time limit. So I'd like to ask your vision on train CNN using MPC, because you show the race car, and when you use train the CNN using certain track, that is an optimized specific data set actually. So I'm wondering if you have a different track, different road condition, then how much that the CNN trained by the MPC will perform well on trained data set. Yeah. So that is a question. Actually, Frank mentioned that the CNN is like local optimization for let it be when you use a let it function. So that is only for specific data set. So I'm wondering on how we train the CNN when we use MPC to cope with the such a situation.
I think it's a very relevant question. First of all, I must caution that in terms of CNNs, we have extremely limited experience. Okay, so up to now, we mostly use feed-forward neural networks and not CNNs. Okay, so I really probably cannot answer this well. But let me answer the second or the related question that you said in terms of the data set and the learning, etc. You know, the question is, why are you doing that learning? Okay, and let me give you an example, and that's a real example actually related to Hyundai. Okay, and related to the work that Francesco Borelli and his laboratory do with Hyundai together on learning. And so what they found, and he presented this also at this MIT workshop that I referred to, they want to address the following problem. If you buy a car in the US, I don't know how it is here, then you get some mileage specifications. Okay, how much mileage what's your mileage for city traffic, etc. But those are some average numbers, and it's not clear what it is. And so what they did actually is they said, we want to mimic a person that is driving to work every day. And the person is somewhere in the Bay Area, is going this, and they go the same track, the same similar time every day. And we actually want to use specifically those data, and we want to have a data-based learning of how that car should be driven in order to improve the consumption of gasoline or the mileage specifically for this track. Okay? Not a general learning of how to improve gas mileage, but specifically for this performance. And it was actually impressive that what improvements they could get, and I don't mean now simulation, but in actual experimental implementation, how much improvement in mileage they could get with specific autonomous driving done in order to improve the gas mileage for a particular direction. So I think that learning of specific data, it may be an advantage for that type of problem. And so I think it depends on the case. But I was very impressed by this application and the experimental results that they were able to obtain.
Okay, so let the microphone goes to the Professor Wook Hyun Kwon.
I have two short questions. The first question is, do you think MPC is a way that we human beings solve a sequential decision making problem in our brain? And the second question is, I personally think we control engineers sometimes put too much emphasis on state equations. And for example, when we solve sequential decision making in our brain, of course we consider state transition. However, we also should refer to, for example, our memory or all kind of experience. So sometimes I think considering state equation only is not strong enough, I guess. So what is your opinion about it?
Fortunately, okay. Fortunately, I have some support for the first question. Namely, the question, is the brain using MPC? And I refer to you, and I can send you the exact reference. There's the television host in the US, Charlie Rose, and he did a sequence of interviews on the brain, okay, some years ago. And specifically, there's a sequence where there's Kendall, and there's Wolpert, and there are two other people, so really recognized expert in the area, and actually Wolpert even makes an experiment in camera to illustrate how the brain does predictive control. So that, I think, is, at least for those tasks, it's documented. The second one I must pass. I think maybe we can discuss more later the specific question. But I think that there's strong evidence on the brain relation side, at least for some tasks. You know. But it's a very, actually, it's a fascinating series and a fascinating type. I highly recommend it.
Thank you. So, is there any questions? Yes, Professor 22.
Manfred, thank you very much for the inspiring talk, and I especially like the way you reviewed the past 50 years. Can you predict forward for real embedded systems, real time? What would be the limit? Can you predict? Based on your model prediction.
Okay. First of all, there is one slide I skipped, okay, which is, however, nothing more than a paper we published a couple years ago that describes and in details analyzes a control law which the title is at megahertz rates. Okay, so in principle, for a linear system with constraints, with a linear rise of a system with constraints, you can, with relatively, this was FPGA hardware, you can go megahertz. And what was our problem in this work? We want to say, we can do megahertz, let's illustrate. We couldn't find an example. Okay? We could not find an example where actually megahertz sampling feedback control was needed. The example we ended up with is not a scanning atomic microscope, atomic force microscope, exactly, sorry. Atomic force microscope, and the scanning rate, and we had a collaboration with IBM in order to speed up that scanning rate, because then obviously it would speed up the whole process. And so that feedback control that you have to do in this STM, we said we can do with MPC. And indeed, because they had actually trouble handling constraints that they were running into. But this was and at least in simulations, it brought improvement, it could solve their problem. But this was arrived at after a long time. So that means, let's say, the simple, non-linear, even control problems, but no switches, etc. I think whatever we have currently available is sufficient. Now, on the other hand, in terms of the switch system and the robotics, people have struggled with this, and we have, and others for at least a decade, and there's still a lot further to go. And one comment that was made by Russ Tedrick, whom I mentioned before, is maybe we are using the wrong approach for those systems. Okay? Maybe this approach of doing optimization, optimal control for this complex system, maybe that's not what has the future. We need to find approximate controllers to deal with it. Because currently it is, you give me a problem that you can solve, I give you 10 problems you cannot solve. So there's the limit there in this area. There's clearly a limit. Otherwise, at least from and I think hardware is not going to solve it, not easily. This problem. Otherwise, I think I'm not sure how much the hardware will. For other problems, I'm not sure how much the hardware will improve. I think it's more of a question of the control context. You know, what can be guaranteed for algorithms, and that is not necessarily just a function of the hardware.
So for the simplest system, 1 megahertz is what you said.
Yeah, for the simplest system, we can do 1 megahertz, and at least if you have some applications that we need more, we would be delighted to hear, but we had hard time finding something that really needed something faster. Physical system, maybe there's some optical system, maybe something where this could be checked. But I think for anything more complicated, like the switch systems, it is still open. It is still open. So those I think are the real challenges which probably have to be addressed in progress in hardware, algorithms, software, and so on.
Okay. So I think we have time for only one more questions. So if you, in particular from the students, if you have some questions, just let us know. Yes, please.
My name is Kim Hyun from Assam Medical Center, and I heard your lecture is very impressive. And I think that the MPC adopted machine learning technique, and I'm very confused that which is the main part, the MPC or the machine learning. And if both parts are equally important, I think that there is some way to adopt the MPC to the machine learning. And how do you think about this point? And my second question is, I heard that you are the pioneer of the MPC. And is there any plan to develop a new theory about control? That's my second question. Thank you.
Thank you for your questions. I think what I can answer more in general is about the medical application that you have alluded to. And we have some experience, okay? Now, and I think the big difference is, in terms of also the learning, do I look at problems that look at images, okay, that were taken from patients, and I'm adapting a method that will improve the diagnosis. So there, I think, at least my impression for specific targeted problems, there's this pathology studies that have been done at Caltech and now also at Sloan Kettering. Actually, a person that I know from Austria, Thomas Fuchs, is leading that effort on computational pathology. I think it is very promising. Okay? But you also probably are aware of investments of AI in the medical field that IBM did with hospitals in the Houston area, where they spent billions, and basically at the end of the billions they said we failed. So I think the medical field, I mean now not online control, I mean offline analysis and learning. It seems that for very focused problems, like I said, the computational pathology for some specific disease, etc., I'm confident that progress can be made, progress that pushes beyond of what a medical doctor can do, okay? In targeted application. In the general application, it doesn't seem it works, okay? And what will also be seen, Deep Brain, they had the medical effort together with the National Health Service in the Great Britain. It was taken out by Google, I guess, putting out, and we will see what it does. So that's the offline. Now we're talking about next online. How can we have control of devices, of medical devices that are actually continuously operating and we want to adapt and so on. I think it's extremely difficult. And despite all the claims, let's say with the diabetes, okay, the automatic pancreas type of concept, there's a lot that has happened. There's progress made. There's nothing close to it. Okay? Right? Even the companies that do that, the closed loop is still not happening. Because there are obvious safety aspects that to address those, and this is all learning, identification, MPC, all of it combined, excellent people, many groups, etc., but it is extremely difficult. And so the automation there will, I think, is still open, and I think on all sides. And I remember I had a student come into my office, actually that was at it was ETH, and she said, yeah, I really want to find out what you're doing there in medical and diabetes because I'm diabetic. And so went to discussion and said about the prediction, and she said, I don't believe at all that you can predict my glucose level, at all. Because she said, I know that if I'm taking an exam, the behavior will be very different than if I run and walk, and to include all that in the prediction will be very difficult. So the closed loop in critical application will be difficult. We had a project for many years on automatic dosing of anesthesia. Okay, so inhalant anesthetics and how to dose them based on some measurements of reflex about response to pain, EMG signals, etc. It has not really come through. Okay, so I think the closed loop still has to wait. I think the offline diagnostic in specific problems, I'm confident that medical doctor will be inferior in those problems very soon, if not already.
Okay, so it's time to wrap up for the day. So, Professor Morari, thank you very much.
Thank you.